Hi everyone. Let's approximate areas of regions under graphs of functions. We are given two regions. We must determine their areas. The first region can be split into two familiar geometrical objects. You can split it into a rectangle and a triangle. The area of the rectangle is 3. The area of the triangle is 3 times 3 times 1/2, which gives us 4.5. Altogether, the area is 7.5. You can't apply the same method in the second picture because the given curve is not straight, which means we don't know the exact area of this region. Instead of finding the exact area, we can try to approximate it. I can draw two geometrical figures inside of this region. I can draw a rectangle and a triangle. I can then compute the areas of these figures. The area of the rectangle is 3. The area of the triangle is 3 times 12, that's 36, times 1/2, which is 18. This tells me that this area of the blue region, is approximately 21. In fact, I know that the area of the entire blue region must be slightly more than 21 because there is a piece of the region I did not account for. There is one more famous way of approximating areas of regions under graphs of functions that uses just rectangles. Let me show you how it goes. First, note that the interval from 0 to 3 is naturally divided into 3 subintervals of equal length. These subintervals will serve as bases of our approximating rectangles. To determine the height of these approximating rectangles, you will choose a point in each subinterval. For now, let us choose the left endpoint of each subinterval. For example, on the subinterval from 0 to 1, the left endpoint is 0. The value of the function at 0 is 1, which means I will draw an approximating rectangle there with the height of 1. Between 1 and 2, the left endpoint is 1. The value of the function at 1 is 7, which means that my second approximating rectangle will have the height of 7. Finally, the third approximating rectangle will have the height of 11, because that is the value of the function at the left endpoint of 2. The areas of these rectangles are 1, 7, and 11. When I add these numbers, I get 1 plus 7 plus 11, which gives me 19. 19 is an approximation for the area of the blue region. I know that this number is definitely an underestimate. And that is because there were pieces of the region that we did not account for. To determine the heights of these rectangles, I used the value of the function at the left endpoints. What would have happened if I used some other point, for example, the right endpoint of each subinterval? On the first subinterval, the right endpoint is 1, the value of the function at 1 is 7, which means that the first approximating rectangle has the height of 7. The second approximating rectangle will have the height of 11, because the value of the function at 2 is 11. Finally, the last approximating rectangle would have the height of 13, because the value of the function at 3 is 13. The areas of these rectangles are 7, 11, and 13. When I add these numbers, I get 7 plus 11 plus 13, which is 31. We know that this is an overestimate for the area of the blue region. And that is because the rectangles included more area than was inside of the blue region. Before we learn how we can improve these approximations, how we can improve these underestimates and overestimates, let's see if we understand how to use the left-endpoint method and the right-endpoint method to approximate areas of regions under graphs of functions. In this problem, we are given a function x squared, and we must find the area of the shaded region from x equal to 1 to x equal to 4 by using 3 rectangles. and first we must use the left-endpoint method, and then we must use the right-endpoint method. If you would like to try this on your own, stop the video now. You can also download these notes using the link in the video description. I will start by using the left-endpoint method. This means I will use 1, 2, and 3 to determine the height of my approximating rectangles. The height of the first approximating rectangle will be given by f of 1. The height of the second rectangle will be given by f of 2. And the height of the third rectangle will be given by f of 3. Which means that the area of the first rectangle is the length of the base, which is 1, times the height, which is given by f of 1. The base of the second rectangle is also 1, the height is given by f of 2. The base of the third rectangle is 1, the height is given by f of 3. This gives me 1 times, and I know f of 1 because I know the formula for my function. When I plug in 1 to this formula, I get 1, which gives me just 1. F of 2 is 4 because 2 squared is 4, which means I get 1 times 4. Finally, I get 1 times 9 because 3 squared is 9. Altogether, I get 1 plus 4 plus 9, that is 14. The left-endpoint method gives me an approximation equal to 14. When I use the right-endpoint method, I get the length of the base of my first approximating rectangle times the height of the first approximating rectangle. The height of the first approximating rectangle is given by the value of the function at 2, which means I have to compute 1 times f of 2. The height of the second approximating rectangle is given by f of 3, which means that the area of that rectangle is 1 times f of 3. The area of the last approximating rectangle will be 1 times f of 4. This means I get 1 times 4 plus 1 times 9 plus 1 times, and 4 squared is 16, so I get 16. This gives me 4 plus 9, that's 13, plus 16, that's 29. The right-endpoint method gives me the approximation of 29. How can we improve our area approximations? This is our original region. When we use the left-endpoint approximation, we got 19. When we use the right-endpoint approximation, we got 31. How can we improve these estimates? There are at least 3 ways in which I know how to improve these. One way is to take the average of the left and the right endpoint approximations. The left endpoint approximation, the left-endpoint method, gave you 19. The right endpoint approximation, the right-endpoint method, gave you 31. If we take the average of these 2 approximations, we will get 19 plus 31 over 2, which is 50 divided by 2, which is 25. This should be a better approximation. We know that the left endpoint approximation was an underestimate. We know that the right endpoint approximation was an overestimate. Taking the average should provide us with a better approximation. The second method to improve our approximations is to use a different point, which we call a sample point, in each subinterval to determine the height of each rectangle. In the left-endpoint method, we use the left endpoint. In the right-endpoint method, we use the right endpoint. But I can use any point I wish in the subinterval from 0 to 1 to determine the height of my approximating rectangle. For example, let us use the midpoint and see what we get. The midpoint is here, and here, and here. The value of the function at the midpoint of the first subinterval appears to be about 4, which means that the height of my first approximating rectangle is 4. The value of the function at the second midpoint seems to be 9, which means that my second approximating rectangle will have the height of 9. Finally, the value of the function at the third midpoint, the midpoint of the third subinterval, appears to be about 12, which means that the height of my last approximating rectangle is 12. using the midpoint method, I get that the area of the first rectangle is 1 times 4. The area of the second rectangle is 1 times 9. The area of the third rectangle is 1 times 12. That gives me 4 plus 9 plus 12. 4 plus 9 is 13. 13 plus 12 is 25. The midpoint method gives us, coincidentally, the same answer as the average of the left and the right endpoint methods. I know that this must be a better approximation because the rectangles miss some pieces of the region, but they also count some pieces that shouldn't be counted, which suggests that maybe the errors cancel each other out. There is one more way of improving our approximations. It is to use more rectangles. Take a look. When I use just 3 rectangles, I miss lots of area. When I use 6 rectangles, I miss less area. When I use 12 rectangles, the area that I miss is very small. This suggests that the more rectangles I use, the better approximation I get. We will explore this idea in one of the future videos. In the next video, I will tell you why finding areas of regions under graphs of functions can be useful.